My name's Oliver. I'm here to talk to you about the last few years of my life. I left Twitter about 18 months ago, and I've been working at a company called Buoyant since then, building an open source product called linkerd. Maybe you've heard of it. Has anyone heard of linkerd? I'm not offended. You will by the end of the day. That's why I'm here. But I joined Twitter in 2010. Anyone using Twitter in 2010? All right, we'll talk a little bit more about that in a second. And it was a kind of messy engineering environment at the time. It was growing really fast. It was chaotic, and we had to figure out how to scale it so that it's the product you know today. And so it was a very full of lessons, full of life lessons those couple of years for me. And I want to talk about some of what I did there. That's my dog. I haven't seen her in a few weeks. I can't wait to go home. I also really, really dislike being woken up by a pager to deal with computers. I feel like that's backwards. Computers work for us. We don't work for them. And so that motivates a lot of what I'm doing nowadays is trying to make computers not wake me up, ever. Hopefully. So we'll start by talking about what it was like to be at Twitter in 2010. How many people have heard the word microservices before? Okay, great.
We don't have buzzword bingo cards.
Okay. And then I'll tell you a little bit about finagle, a project that Twitter open sourced. People hear of finagle? Great. And then linkerd. And then if the Wi-Fi gods are happy and smiling on me, we'll do a demo. And then after all that, we can do a Q&A. But if you have a burning question, please just raise your hand, and I'll try to answer it. All right, clear your minds. Put yourself back in 2010, simpler times. So I joined Twitter in about August 2010, and this is the growth curve of what it looked like going to that. So it was growing really quickly, right? Maybe too quickly. And that is not just the users, it's also the number of engineers, the number of services, the number of deploys, the number of features. Everything was moving really quickly. And with that, there was a lot of visible pain. So if you were on Twitter in 2010, you probably saw a whale a lot of the time. And that was kind of what this was cute about the service, right? But we didn't really have our own data centers. There was one team responsible for doing every deploy. There was one Rails stack, which got deployed, and that was everything, the whole site, everything you know. And it was painful. That team that did deploys didn't really have free time. Deploys would go bad, and everyone's features would get rolled back. It was a lot of high-friction environment to move quickly. And Twitter, if you remember, didn't have pictures. There was a star button. You could click it, but nobody knew what it did. Manual RTs, like everything was totally different. It was a different product then. And we're trying to figure out how do we actually make this product real without breaking the site constantly. And if we're doubling the size of engineering every 6 months, how do we move quickly together so we're not stepping on each other's toes? Another big thing in 2010 is the World Cup. This is actually what really hooked me on Twitter, and when I realized I wanted to work there, is because every time there was a goal, the site would go down. And so the stories of Twitter engineering saying 0-0 draw, 0-0 draw, just sitting there like no goals, please Germany, no, don't score, right? Because every time it happened, it was just whomp, site down, whaling, roboting. Robots are 502s or 503s, and whales are 502s, were. And so this was the first time I realized the kind of global impact of Twitter, that everyone was enjoying this event together at once, and all reacting to it made operational pain. Like, that is what I want to go work on. I want to go be in the middle of all that, where there's problems to fix. So that's really what sold me on joining Twitter, and I applied in July or August of that year. And you saw a lot of this, right? You haven't seen this in at least 3 or 4 years. This was what made Twitter famous. This is why it was OK to use Twitter when it was down, because you just keep reloading, keep reloading. And you haven't seen this in years. Now it's a newsworthy event if Twitter's down for more than a few minutes. How do you do that? Well, you just add more hardware, right? You add more hardware, you deploy it, you put some load balancers in there, and everything's going to work, and maybe some caches. And that was what Twitter did. It was like, we're going to add caches at every single layer of the stack. More caches, more caches. Well, when the caches go down, what happens? Right? This was not a great story. And so what's hard about Twitter is different from other sites. It's not just scale out horizontally. It's that Twitter is unpredictable. So here's a wave we rode in 2013. This is the graph, actual tweet per second graph, or tweet per minute graph, of an event in Japan. And what happened was there was a movie broadcast nationwide on TV, where at one point in the movie they say, "Everybody tweet now." They didn't tell us about this in advance, right? We didn't know this was coming. It was just like, all of Japan is tweeting, and everyone in Japan at the time had 2 devices, so they're tweeting from both devices. How do you provision for this? How do you build a system where you're going at some nominal 200, or was it 20,000 tweets per minute? How do you provision for a peak that's an order of magnitude larger? You just buy an order of magnitude more hardware and say, all right, eat the costs, we'll deal with it. Any elastic scaling is not going to work in this type of instantaneous time frame. So how do we build systems that are able to at least absorb and resist this kind of stress? It wasn't easy. Another really interesting problem of Twitter that you may not think about is the kind of asymmetric nature of following. So I maybe have a couple thousand followers. If you're Kelsey, you maybe have 20,000 followers. If you're the CEO of Twitter, maybe, 2 million, 4 million followers. If you're any of these people, we're talking like 80 million followers, right? These are huge, vastly different scales. And so when one of these person tweets, it has to fan out and do a lot more work than when I tweet. And this makes it really hard to provision. So there's this kind of cute story, which people took literally, that we were having dedicated racks for Bieber. It didn't actually happen. There was some special case code, I think, that said if user ID is Bieber. But generally, right, we had to think about how to do fan out, how to do queuing, how to manage these things differently. Because back in the day when Ellen tweeted, it would take 30 minutes for it to get to all our followers. And that's not an instantaneous experience. And Twitter is about instantaneous experiences. And so this is a real challenge. And then maybe a more mundane challenge, provisioning. This is Oliver Twist here, asking for more hardware. And so this is actually a really real problem. When we started, we didn't own a data center. We were renting hardware at another data center. And we were going into 2011, we're like, we need more hardware. And they said, no. Like, you go to your data center provider and you're like, I need more boxes to run twitter.com. And they say no. So what do? You start to play games of like, OK, I know the person who owns the spreadsheet that gives out hardware. I know he really likes Bullet Rye. I'll bring him some Bullet, and maybe this will all work out. And that actually is how some people got hardware. I was on the ops team, so I could just give myself hardware, which was a nice feature. But that didn't scale. And so this is kind of what led to the experiences of now having Mesos and Aurora. If you've heard of these projects, this is the orchestration layer that Twitter developed. If they were starting today, I would hope they wouldn't build this all, but we kind of had to at the time. We knew about Borg. We had a bunch of very smart ex-Google engineers, and ex-Google engineers like to go rebuild Google. So we built Mesos and Aurora. And that really kind of enabled us to not deal in this very slow, month-long hardware acquisition process. It allowed me to say, I have an idea, I want to run a new service, and from code complete to running in a prod-like environment is like 2 minutes. No hardware costs, right? And so that's a much more iterative, flexible, quick environment. And so that's kind of the basis for where Twitter was starting at, to what the big engineering problems were. And some of these are organizational problems. They're not all technical. And that kind of leads us to microservices. So Twitter, I worked at Twitter for 4.5 years. I never once heard this word. And then I went to leave and start a company, and I'm talking to somebody like, oh, you're talking about microservices. What? I'm talking about SOA. I'm like, no, you can't use that word anymore. Please, no. Nobody wants to hear that word anymore. There's some trauma there. And so we started to, now I know what microservices are, but really what we're talking about are, well, who wants to tell me what a microservice is? Somebody has what's a microservice?
Oh.
Yeah, what's a microservice?
Distributed perfect functions.
That's a pretty good, yeah. The answer I get every time is really tiny services. which is also true, but not maybe depending on what you mean by tiny. So I think about these not in terms of footprint or memory usage or CPU or how many instances you have. These are about scope, right, and constraining scope. Marius, a colleague of mine at Twitter who left recently, wrote a paper called "Your Server is a Function," and this is that idea, right? That we constrain scopes so that not only is it easy to think about, but it's easy to operate. When I started, we had one on-call rotation, ops on call. I was ops on call. Somebody else was engineering on call. And when things broke, you had no idea about this code. You'd never seen this before. You'd never touched it. And so we had to do the SRE thing, right? We had to kind of decompose things so that I could write code, and then if it broke that night, I woke up. Hopefully not the rest of the company. And this is this autonomous nature. Maybe some people call that DevOps. DevOps is a lot of things, but this is kind of what motivated us into microservices. And so this is about scaling teams and growing the software, being able to be iterative in our building the system, but really, really, really about scaling teams. It's about flexibility, right? That somebody else's deploy schedule doesn't impact my deploy schedule. Somebody else's incident doesn't interrupt my night, hopefully. This is about letting people work independently and having the organization be able to be more agile and more flexible. So microservices are not a technical solution. Just going to say that. When you go to microservices, you give up a lot of things you're used to, right? All of these things you do not get for free by going to microservices. You'll read blog posts that kind of hint that, like, once you're in this Google world, this Giphy Google for everyone, everything's great. No, Google spent decades developing the infrastructure and tools that they need to operate these things. Now we're starting to see some of this in Kubernetes, et cetera. And we really lose control, right? Where do I go tail a log file? Where do I TCP dump? Everything is a network call now. How do I reason about this? How do I S-trace things? All the tools we're used to of logging into the web server, running a few admin commands, and then getting answers, I don't have those tools anymore. And so we have to reimagine what those are. They're hard. Microservices are hard. If you don't have to do them, if you're not working in a growing organization, do not do them. This is about growing the organization. This is a quote from Marius, who I just mentioned. Resilience is an imperative. Our software runs on truly dismal computers we call data centers. Besides being heinously complex, they are unreliable and prone to operator error. So think about this for a second. If I could run Twitter on a mainframe, and I gave this mainframe perfect power, perfect cooling, a billion cores, a billion gigs of RAM, why wouldn't I do that? No reason not to do that, right? I just want the application to run somewhere. If it's reliable, we'll do that. We don't have these magic bullet mainframes. They don't exist. And so what we have are warehouse computers, where we buy a lot of commodity hardware and we let them die. We let hardware die, and that's just the nature of things. This is the cloud, right? But what that means is we have to admit failure, that things will break. We cannot make the box stand up perfectly. We can't make the power perfect. We have to admit that things will break at unexpected parts of the stack, and it's on us as application owners to own that failure, to accept that it's going to happen and be ready for it. And so we think about resilience in microservices, we mean there's going to be a kernel bug. I mean, I have never even talked to the network engineer. I don't know where they live or who they are. These things are going to break during the Super Bowl, during the MTV VMAs, during the Emmys, and we can't just have the site be down. This is about business continuity, right? Being able to keep doing some amount of business when things you didn't write, that you didn't know existed, break. Quick aside, this is just, there was a kernel bug that we had at Twitter where if a box was up for 394 days, load would spike to 3,000%. This is, so we had to reboot hardware. We had this clicking clock of all of the machines and their uptime. And around 300 days, we really had to start rebooting it, or else we were getting a risk. So this was before we had Mesos, this was a huge, OK, move all your applications off this box onto other boxes so we can power cycle it overnight. And when it comes back up, you bring it. And like that, nobody has time for that. This stuff's going to break. assume it's going to break. Don't build your application around specific pieces of hardware. And back into microservices, this is about communication, right? Where we had library calls, we now have network calls. When I have a network, things are going to break, and things are going to break weird. And so this is the way I kind of conceptualize what we have, and maybe what we haven't talked about. So down at the bottom, we have the Ethernet cable that's being run into the rack. Anyone still running an Ethernet cable manually? I'm sorry. And then we have some DHCP servers that configure IP addresses, and maybe we have some virtualized IP space now with Canal or Weave doing container networking. And at the top of this, we end up with some orchestration layer. And this orchestration layer, if you're not in Kubernetes or Mesos, is really going to be your deploy script, right? The thing that uploads, maybe Puppet, the thing that puts your code on the server and gets it running. At the end of that, all that can really do is get sockets up and running and listening. And so we now can accept connections. That's all that gives us is we got a service, it's listening, it's ready to do business. At the top of this, we have layer 7. Now, I hear about layer 7 load balancing. I hear about layer 7 infer things all the time. I want to distinguish that. Layer 7 is your code. Layer 7 is tweets. Layer 7 is bike rides, money changing hands, the things that your application owners should be thinking about. Your application owners shouldn't be thinking about connections and buffering and retries and the things that are kind of details of how I fetch a tweet. Fetching a tweet is, I want a tweet. Give me a tweet. Not, OK, and if I can't get the tweet, please retry 3 times and do exponential backoff and do service discovery. There's all these details in here. And that's what we think about, what I think about at layer 5. So layer 6, we're talking about presentation. We're talking about JSON, thrift, protobuf, whatever you're doing to encode things, XML. Anyone doing XML? And then at layer 5, what we're really dealing with is mapping these things onto connections. So to say, I want the please write a tweet request up at layer 7, turns into some thrift object at layer 6. And now, where do I deliver this? And so at layer 5, we're dealing with, I have connections. Which connection gets this request? And if this fails, how do I retry it? And what's my SLA on this request? Right? So this is all things that we shouldn't be solving in every application. And when I started at Twitter, I was writing, I'm a part of the monitoring stack, and I was writing connection pooling, load balancing, retries, timeouts. And the person next to me was writing a Jetty server, and she was worried about connection pooling, retries, deadlines, timeouts, all these things. And every application owner and every different piece of the company had to solve these things. And so we kind of had this realization that this isn't going to scale. We're not going to grow the company and everyone reinventing this stuff slightly differently in every application. And so we need to stratify this and bring this down into another layer that's not at the business layer. Everyone get this so far? We're doing good? Great. And so at layer 5, we're talking again about requests onto connections. Layer 4 is where we have our TCP. Everything's easy to think about. At layer 5, we have to make some decisions around how we do delivery and how we have reliability there. All right, and that brings me to finagle. Finagle is an open source library for a weird class of people, to be honest. I'm part of this weird class of people. You have to be hipster enough to want a strongly typed functional language, but fuddy-duddy enough to be on the JVM. And this actually was kind of I went to Twitter, and I'd never seen anyone write a performant application in Java before, and I was like, you're going to what? You're doing what? And I learned that actually there are a class of very high performance applications in the JVM. We have frameworks like Netty, which is a highly used JVM library for doing networking. It powers Apple, Netflix, Twitter, a lot of the big names. And it's literally doing trillions of requests a day, easily. And so Twitter started building on Netty. We hired one of the Netty core committers, and Nick Kalin and Marius Eriksson were working on a project that eventually failed, but they salvaged this nice core library out of this failed project that we call finagle. It's used at a large number of companies nowadays. New York Times, I saw someone here earlier. I think New York Times has some of this. Obviously, Twitter is the major development force behind this. But there are a number of other companies. I think SoundCloud spoke about finagle earlier today. And most of these people are adopting it for the programming model. Again, this weird fuddy-duddy hipster crowd, where we want this nice, functional, asynchronous, predictable way. And this is maybe the prototypical service at Twitter. I have two clients. I have a client to the user service and the timeline service. I open a web server. I take requests, and I issue them asynchronously. And you don't see any of these details, timeouts, retries, backoffs. None of that's here. Service discovery, none of it's really here. So I had this nice programming model that's easy to think about, easy to test. It's statically typed, so it's predictable. And this is why all these companies are adopting finagle for the most part. We have these nice abstractions. Async, again, services as a function. We have this kind of asynchronous, give me a request, give me a response. We have this for connections as well. Given a connection, give me a service. And we have filters, so I have a way to compose functionality onto this. This lets me write layer orthogonal pieces of code. So I can layer timeouts and I can layer retries around my service. And this can work on the client or the server. So we have a very nice set of reusable primitives. But this isn't really what I'm here to talk about today. I'm here to talk about the operational bit of finagle. Me, as an ops person, being on call, what do I get out of finagle if I'm not writing services myself? I get a whole bunch of predictable things that I can go to any application and I can ask it about its success rate. I know how to reason about its retry policies. I know how to monitor it, right? So we now have a bunch of common things that are operational benefits that application owners don't have to think about when they're writing code. But as we go to production, we can just plug into it and be ready to be on call for this. It really does reduce a lot, especially when we're talking about monitoring, debugging, testing, a lot of the things that are afterthoughts of the development cycle. One of these first things we deal with in any complex microservice is staging. So I have some services up top, right? We have a web layer, which does all the front-end stuff. And then I have a few composition services, like timelines or followers, following graph. And then all of these things talk to a user service at some point, right, that encapsulate the user database. When I want to launch a new version of the user service, how do I test it? Do you think I can run Twitter on my laptop? There's not enough memory in the world. Well, there is, but not in a laptop. We just can't do it. There's too much JVM. And so we have to find a way to stage this. And so we started by saying, oh, I have a staging data center. Everyone will deploy to the staging data center. It'll be great. No. Nope. Staging data center, no one actually wants to test there because it's against a bunch of broken code. People want to test in the context of production. How is this actually going to run when I go? So staging data center languishes. It really rusts quickly. And so we had to figure out how do we do testing not on my laptop, not going to run anything on my laptop, not in a staging data center. I need to do this basically in prod. And we need to do this in a controlled way so that I can have all of my services above me, all of the clients to my service, know to talk to the staging service when appropriate. And so we introduced this abstraction, this naming abstraction. And so in that code before, you didn't see anything about Zookeeper or service discovery. You saw, I want to talk to the user service. The user service might be the staging user service in some context. On my laptop, it might be a local port. In prod, it's going to be one version of the service, and I might want to change what version of the service that's on. And so this is a contextual decision. I write my code against these kind of logical names, and then as I'm binding my clients, as I'm sending requests, I'm binding these down to some concrete version, which is this version of this service, which is these sets of addresses. This lets us do some very interesting things, because I can even do these I can pass this context on a per request basis. And this is my last project at Twitter was getting the staging system into production. At the time, we had 250 host names, and you'd pick a number between 1 to 50. You'd grab that host name and hope no one was using it, and you deploy all your staging stuff into that namespace. It doesn't scale, because there are thousands of engineers at Twitter now. So we had to figure out a way to give people more flexibility to, OK, I'm Oliver. I'm going to launch Ver's service, and it's up and running. And I don't have to coordinate with everyone around me to point clients at Ver's service. I can say, when you, on this request that I'm going to twitter.com, instead of talking to the user service, talk to Oliver's version of the user service for anything in the call graph. And so we did a Hack Week project where you go to twitter.com, you set a cookie in your browser. I only see employees. I wrote a version of the user service that didn't know about non-employees, and I can actually build filters around other services this way. We can also build proxies, right? So I can do staging. I can also have a debug proxy that maybe inspects the payload and dumps a bunch of debug information, or injects failure or timeouts. And so I can do this on a very controlled basis and say, on this class of requests, go through this other proxy before you talk to your service. And we can inject functionality here. And so going back to my analogy earlier about strace, this is now a way to do kind of call graph interception at the data center level. So not at the library level where we're dealing with syscalls and things like that, but in between services, how do I intercept and debug calls? This is a mechanism for that. All right, so we got through staging. The next big problem, maybe you've seen Jeff's talk before about, or it's a blog post as well, Notes on Distributed Systems for Youngbloods. But there's a lot of truth in this, and I hope that's widely accepted. But it's slow is the hardest problem. It's down, just bring it back up. Get new hardware. It's slow, I don't know. And it's slow for some class of things that I don't fully understand is even weirder. So when the CEO comes down and says, well, when Kim Kardashian tweets, users don't see it for a while. When I tweet, it's instantaneous. How do I start to debug these things? So in a distributed system, we have a bunch of complex connections, right? We don't have one-to-one relationships anymore. We have M-to-N relationships. And so when a service becomes slow, it's not proportional to slowness downstream. Failure cascades and spreads. In fact, it's very complex. This is a real view of the call graph at Twitter some 3 or 4 years ago. Our team, my observability team, open source Zipkin, which is now maintained as open in a foundation, not by Twitter. And this is a tracing system that we use to start doing debugging and have debugging tools in this complex environment. And so the first thing we get are kind of nice call graphs, right? Being able to say, oh, I'm spending this much time in each call. And this call comes before that call. So we see some serial calls here. Can those be parallelized? Is 20 milliseconds in this one call too long? And so this gives us some ways to start doing performance debugging in production by, OK, show me the class of slow requests. Let's go look at some actual instances of those slow requests. Furthermore, we had this nice problem where we didn't even know what services were talking to each other necessarily. And so we go to an incident and say, oh, who's talking to me? And we'd have to go look at logs and figure things out. It was really hard. So we did what most organizations do, and they put a project manager on it. No offense to project managers. Some of my best friends are project managers. But the tool a project manager has is a spreadsheet, for the most part. And so we started going around team to team and say, OK, please enumerate all of your dependencies. We do that. A month passes. We go to an incident, and it's wrong. The spreadsheet's wrong? How did that happen? Well, we did a deploy last week, and I added this new dependency because I was trying to test this integration for our contract with whoever. And so this is a fluid thing, and being prescriptive about relationships is really hard. We can't ask a question. We need to ask the system, tell me who's talking to each other. And so tracing gives us a way to deal with these dependencies in a descriptive way, not a prescriptive way. Where in an incident, I can go and say, show me all of the clients of this service, and it's obvious. And the request volumes, and the failure rates, and these sorts of things. And so once we've found out that something's slow, how do we just avoid that? Slowness is bad. So the sharpest tool we have in our toolkit is load balancing. And this is something finagle does actually very well. And so most load balancers that you're familiar with are connection-oriented. And that means either round robin or least loaded, fewest connections. That's a pretty crude tool for doing load balancing. And so at Twitter, in finagle, since we can look at request latency, we can say this is how long this request takes. We can use actual latency to inform load balancing. So if I have a node that's healthy and really fast, I'm going to send more load to it than I will the slow nodes. Or if I have a node that's really slow, I'll send less load to it. And this actually helped deploys. We had deploys that would take 6 hours, and this brings them down to about an hour. Like, this is a big tool. In this example here, if this graph is visible on the slide deck, what we did is we ran some load balancing tests on various algorithms with round robin, which is HA proxy, Nginx, all these things use that, or F5. We set a timeout of 1 second. And then we had one node fall out of SLA in a 10-node cluster. Round robin puts us into 95% success rate. In most on-call rotations, that's a wake me up success rate. I don't like to be woken up, so let's find a better load balancing algorithm. Twitter did a bunch of work to get UMA, exponentially weighted moving average, which looks at latency and punishes slow nodes. With this same test, just switching load balancing algorithms, we're up above 3 nines, which in many cases is not a wake me up success rate. That's an improvement. Furthermore, we may talk to very large clusters. I may talk to, the user service may have 1,000 nodes. If I'm not doing at least 1,000 QPS, or 1,000 concurrent requests, load balancing isn't going to help me. I don't have good information on load. And so we need actually a way to constrain the number of nodes I'm talking to or considering, and that's the aperture load balancer. And so these are things that have been developed in finagle. They're open source and available to look at today. That really helped reliability at Twitter. That like things can break, and we'll just kind of send load around it. Not the end of the world. We're not going to fail things. OK, and so once we have load balancing, we have to start thinking about SLA. And so we start with timeouts and retries. These are very easy tools to apply. So maybe we start and we say, OK, and these are all different services. So the user service has a set of timeouts, and one client of the user service has another set of timeouts, another client has another set of timeouts. And so we pick these things and we set them up with some number of retries. Anyone see any issues with this? Yeah, and different number of retries, right? Basically, nothing below the top one matters. The top one's going to be more restrictive, and will just cancel things out before any of the other retries can apply. And this gets very hard to coordinate. So we'd have like fire drills where we get all the tech leads in a room, and we try to negotiate timeouts with the whiteboard. It doesn't work. It works up to a point, but it's not a scalable way to solve this problem. And so we started thinking about deadlines instead. And this lets us do feature-level load grants, right? I can say, well, I'm willing to give who to follow this amount of latency, but maybe tweets I'll give longer latency, right? And so I can actually set things high up in the stack and let those timeouts propagate with the request. And we just reduce the amount of time on every hop. This can be a very powerful tool. This is all instrumented in finagle. Similarly, we have retries. If I set retries to 3, what does that mean, right? That means when things are going badly, I've made an error cannon, right? Retries just say do more work, put more load on the system. And so a retry of 3 is 300% more load. When things are actually breaking, that's worse. I've made the system worse by retrying. And so we took another approach here and said, well, what if we set budgets? I'm willing to add this much more capacity on the system. And so by default, finagle says, OK, I have a 20% overhead of I'm willing to do 20% more work to satisfy retries. And so as we get requests, we say, oh, put a token in the bucket, put a token in the bucket. When we have an error, if I can retry it, I can take a token out of the bucket, and I can retry up to some level. This becomes, again, a much more intuitive way to manage load in your system. Finally, once we actually have this ability to do timeouts and retries, we also have to think about what happens when I time out. So let's say the timeline service times out. We actually have more work going on in the system, right? The user service might be doing thousands of requests against the database to satisfy that. I can just cancel that and let it go. Or I can knack that. And so we actually have a way to cancel the work and requeue. So we actually get a whole bunch of operational value just out of finagle. Phil, DigitalOcean, tweeted this a couple weeks ago. It's very true. So just please adopt my weird hipster fuddy-duddy lifestyle and write everything finagle. No? OK. Well, we wrote linkerd to solve that problem. And so linkerd is an open source proxy. It encodes a lot of this value. You just send your requests through it, and it deals with service discovery, telemetry, getting tracing and stats out of this, retries, timeouts, all these things we've been talking about today. It's pluggable, so we have integrations with Consul, etcd, Kubernetes, Marathon, Zookeeper, etc. And you can set this up in a kind of per host model where everything on that host talks to a linkerd. Linkerd can manage TLS, do protocol upgrades, do NACking, all of these things for you. And it has nameRD, which is, again, when I was talking about that routing policy, we can store that somewhere central so I can go to one API and change routing policy for my entire data center. And so we have all of the linkerds, set watches on nameRD, which is backed by some service discovery mechanism. And this is how we can do kind of global traffic management, or at least data center level traffic management. All right, so I'm going to rush through a demo really quick. Strap in. OK, Job. So everyone know who Job is? OK, Job wrote a really dumb program in the show Arrested Development. It's really dumb. And so I've written it for Kubernetes to be infinitely scalable in the internet. Main thing about Kubernetes is we have this nice model called pods where I can have multiple containers living in a single kind of hostish abstraction, even though it's not a host. And so we do this, we deploy linkerd and the application in each pod. So it's basically an outsourced network stack. We have service discovery built in here, so I have services that I can select over pods. And OK, so we have a web service and 2 backend services. The word service is a dumb dictionary, and the gen service just repeats things infinitely, or up to some limit. And I'm going to launch a new version of the services, and I do so in a controlled way. And this whole demo is open source, so go there later, do this yourself. OK, so we curl this. I get different dumb words every time. What we see here, I gotta refresh, sorry about that. This is the running linkerd on the web front end. We should see some requests coming through here if my internet's working. Yep, we see some requests coming through here. We have a few clients, the gen and the word service. I've already launched these things. So now what I want to do is stage something. I have a new version of the gen service, and I want to, just on this request, stage a new version of it. And I get a different result, right? So if I go back here, nothing, add this one little override to it, and I've rewritten where the request goes. It goes to the new version of the service. Here we see that the client's been automatically configured. We've discovered this. There's been no configuration for this. It all just works. And so now I've done staging, right? I've done some ad hoc staging. And now I want to canary this out into production. And so what I'm going to do is go over here to my handy-dandy D tab and put 10% of the traffic onto the new versions of the service. I'm going to upload it to nameRD. And what we see here is that we see load instantaneously come out of the new thing. So we've taken 10% of load off the old services, 10% of it's going into the new services. Everything's good, right? Maybe not. Maybe I deployed a bad thing. So I have 80% success rate. Well, let's just ignore that for now. We're moving fast. All right, so I'm just going to go through, and I could do a bunch of kind of incremental upgrades here, but what I'm going to do is just skip and say we're going to go full hog to the new version of the service. And if for some reason it disappears, we are going to fall back. I update that. Boom, all the traffic's going to fall over. Sorry, all the traffic falls over immediately. We're on the new version of the service. Got clients provisioned. Still have that success rate issue. However, my top line success rate is still 100. So I'm 80% success rate of the service, but we're papering this over with retries. So because I know idempotent requests are retriable, and these are gets, I'm able to just retry them freely. And so this is papering or fixing a problem in the system for us. OK, I finally actually realized that I have a terrible success rate, and we need to roll that back. So what I'm going to do is, well, I could just take it out of here. Alternatively, I can do just going to tear it out. Just delete the whole thing. Delete the service for it as well. And we bring all the traffic back on a new version of the service just by failing over. So we have a great way to do staging, canary, and traffic management in incidents. All right. And just to wrap up quickly, this is, again, open source demo. Go for it. We have a bunch of work ongoing here. I'm testing gRPC support now. I'm really excited about gRPC, and linkerd is going to fit great into this. So I think in October, after the next finagle release, we'll have a beta of that available. I may even publish a binary earlier if you are nice to me. We have deadline enforcement. Right now we propagate deadlines but don't act on them. We're going to turn that on soon. We want to do dark traffic so we can do T and compare results. And we want to, basically, linkerd is a configuration layer over finagle. You don't have to write a bunch of code. You have to write a little bit of YAML. And so our main challenge is how do we expose these kind of complex operational details in a little bit of an easy to understand config. And so that's really what we're trying to do, is free a lot of the operational value in finagle into a config file so that you have something that works across languages by default. All right, thank you very much. Beautiful website there, linkerd.io. Join our Slack. Bother me there, or don't bother me, say hi. Email me, follow me on Twitter. And with that, I think I have a second for questions. Yeah.